All right, so let's get started. So this is an interesting thing. We've started out, we went to the mountaintop, a couple of mountaintops so far. The first one was sort of the quantum nature of statistical thermodynamics, and looking at how from the very energy levels we can add those up and get that equipartition theorem of energy and the heat capacity. So we sort of the pinnacle of that one was not just coming up with the internal energy, enthalpy, Helmholtz energy, Gibbs energy, all of those different things, and even the equilibrium constant from quantum states, but also an understanding of how materials interact with heat, because we use those things in heat engines. And that was the next sort of mountaintop. Climbed up and looked at the Carnot cycle, sort of the maximum theoretical efficiency, and we saw that that heat capacity that we developed in the first piece was related to the second piece, and that if you had different heat capacities, different molecular motions, different rotations, different translations, you would have different performance on the engines. Now we're going to take a transition away from using just gases to drive our heat engines and look at all the other phases. And so this whole section is phase diagrams. Everything we've done so far has been in the gas phase. So all of those engines, even all of our translation, rotation, and vibrational degrees of freedom, those are for single particles in the gas phase. So now we're going to start talking about condensation and solidification, sublimation, all of those different phase transitions. Before we start that though, we'll start going from the ideal gas, which we've really been using the ideal gas model, to real gases. And so that's today's lecture. And I got new batteries, so I think it's actually the remote that's busted. So it's just real finicky. It's got to be in the right position, I think. Okay, so just to refresh your memory, we have different standard conditions. So standard ambient temperature and pressure would be 298 Kelvin and 1 bar. Whereas standard temperature and pressure for gases was 0 C and 1 atmosphere. So essentially ice water. So it was really easy for us to get those standard temperature and pressure conditions in the past. We just had to put things in an ice bath. And we're dealing with gases, and so gases at STP, you can figure out how many moles you had. That's actually how they did stoichiometry at the beginning. They would have gas phase reactions, and they'd look at the changes in pressure, and they would relate that to moles. How did you standardize those variables? Well, one of the ways is to hold down the temperature and the pressure. You could do the pressure with a manometer. You could do the temperature with an ice bath. Notice how, if you've memorized the molar volume as 22.4, that's not going to be accurate at standard ambient temperature and pressure. So that's another reason I show this, so don't just jump to the molar volume being 22.4 liters. That's pressure and temperature dependent. And so if we have a different temperature and pressure, we've got a different molar volume. And so for standard ambient temperature and pressure, it's 24.7, so quite a bit different. Okay, so then we look at Dalton's Law. This is one of the things that is going to hold throughout our course. We will show later for sure that Raoult's law breaks down. Raoult's law is that the pressure of a substance is just, the mole fraction of that substance times its pure vapor pressure. So you can look up the vapor pressure for water, you can look up the vapor pressure for CO2, and all of these things would have a vapor pressure at a given temperature. And if you're 50% concentrated, then Raoult's law just says you have 50% of that saturated vapor pressure. So this is a pretty simple linear fit, and those crisscross lines would be Raoult's law. And Raoult's law fails miserably when you're in mixtures. So you have Henry's law that dominates in dilute mixtures, and Raoult's law that dominates in concentrated, on the concentrated side, and we'll get into that much more later. But the point is that we're pretty confident that Dalton's law is still good. So in the gas phase, the particles don't interact very much. And so you can just add up the partial pressures to get the total pressure. And so we will use Dalton's law. It's going to still be good no matter what the mixtures do. And Dalton's law is just that the pressure, total pressure, is the sum of all the partial pressures. So you can see that right here. So the total pressure in a container is just the sum of all the partial pressures. So that one we're going to definitely use. And a lot of times that one's not stated, that's just something you have to know. So if you have the partial pressure of all these different gases, you can add them up. And if you want to know what the individual pressures are and you've got the total pressure, then you can do some subtraction and get the individual pressures. Now the mole fraction is the number of moles of substance J here divided by the total number of moles. What if you don't really know the moles, but you could figure out some way to measure the partial pressures? So if you have the partial pressure divided by the total pressure, that's still going to be the mole fraction. Mole fraction is going to be from 0 to 1, right? And if you multiply those percents by 100%, then you're going to get the mole percent. So we'll deal in mole fraction quite a bit, especially when we get into the mixtures. I just show you this mainly so we're talking about real gases, and I want to emphasize Dalton's law. But we'll come back to these mixtures. We're not going to do the phase diagrams of mixtures first. We're going to do just pure substances. So we're going to get away from mixtures now. I just wanted to show you this one screen to show you Dalton's law, essentially. And then we're going to go into pure substances next. Let's think about the gas model that we've been using. We've been using the ideal gas model, which meant there were no attractions or repulsions. The only time we had repulsions is if the two gas particles tried to occupy the same space. And so these were called point masses. So all of the mass of the molecule, so water, all 18 grams per mole was occupying the center of mass coordinate in the room. And there were no attractions or repulsions between water molecules until they actually tried to occupy the same space, and then you'd have a collision, and it would be a purely elastic collision. No energy would be redistributed into the vibrations or the rotations. So for the ideal gas, there's no interactions, there's elastic collisions. And so that's what we have with that orange curve, the ideal gas. So notice that the energy on the y-axis is 0 until they hit, and then it essentially goes up to infinity. So no matter how hard they hit, they're going to come away with the same energy. They're going to bounce off, and those would be called hard particles and point masses. Those are some of the language, some of the words that we use for an ideal gas. But what happens with a real gas? As they get close to each other, so follow the blue curve. At infinite separation, there's 0 potential energy between the molecules. But as they get closer and closer together, what happens? The first things that interact is the electron cloud. And electron clouds oscillate all the time, and they cancel the positive charge of the nuclei. So as the molecules get together, they get closer together, the electron clouds start interacting and start repelling each other. Well, because they oscillate, there's a chance that you would have an induced dipole moment. So it's kind of like a game of chicken. Whichever electron cloud flinches first, then that part of the molecule becomes positive just for an instant. And so this electron cloud moves out of the way, and this one now sees the positive nuclei and is drawn close. But the clouds have to oscillate. So this electron density that moves towards the positive charge can't stay there forever, and so it oscillates to the other side of the molecule while this one splashes towards the positive. And so you get this attraction by an instantaneous dipole moment. And that happens in every atom. Even helium, even hydrogen molecule. So even things with very, very small electron clouds will have these instantaneous dipole moments. Now you get bigger instantaneous dipole moments, the bigger the electron cloud. So for chlorine, it's much more polarizable than for hydrogen or for helium. So the bigger the molecule, the bigger the electron cloud. And the bigger the electron cloud, the more of these instantaneous dipole forces will cause attraction between the molecules. And so then you have a more opportunity for attractions. And if you go down in energy, then that's beneficial to the molecule. They start becoming attracted to each other. Okay. But if you get too close, then the electrons slosh away and you see the nuclei start to see each other, and the positive charges repel, and they're not polarizable. They don't go anywhere. And so then you get a hard repulsion. So if you compress a gas too much, eventually the repulsions dominate. They're hitting each other too hard, The nuclei are seeing each other in those collisions, and they come off with a large amount of energy. So you have a positive repulsive part of the region, a part of the interaction. So here's the repulsive part where repulsions dominate here, and here's attraction dominating. So if you have the sweet spot of the average separation between your molecules to be right there, so if this is the gas phase, now this is the same kind of thing we have for a diatomic bonding diagram, right? But that's not what we're talking about here. We're talking about gas molecules interacting with gas molecules. So this attraction is not as strong as a covalent bond, but you could draw this same diagram for I2 like we did for iodine. But this is much weaker than a covalent bond. This is just two molecules in the gas phase being attracted to each other. And if you're in that sweet spot, then you have a high probability of condensation, so that these molecules are attracted to each other enough to stick to each other, and then another one comes along and sticks, and you have nucleation. You start to have droplets of liquid. So all you have to do to get a gas to condense is compress it and sink the heat, take away the excess heat, and then things cool down, they stick to each other, and they start to condense. And it's because of those London dispersion forces. Now, that's going to give you the different boiling points of all of your noble gases. So over here, the helium through xenon and so on. Those larger atoms are going to have a higher boiling point. They're going to condense at a higher temperature because of these instantaneous dipole moments. Then you put in something that has a dipole moment, and it condenses even easier because they've got a permanent dipole moment. And then if you take water, which has hydrogen bonding, it's going to condense at even a higher temperature. Water, it's really crazy for water to have a boiling point of 100 C or 373 Kelvin because it's only 18 grams per mole, and it doesn't have a large electron cloud, but it has that dipole, that hydrogen bonding character, and so it has a very unusual boiling point. So let's think about the behavior of gases. We have used these PV plots, and we had isotherms and adiabats, and we were just working with this in the Carnot cycle. And so you might have, like the one we had in on the recent exam, we had an adiabat here, like that, and an adiabat here, like that. And so this might be the Carnot cycle. We have A, B, C, and D. And you can see the adiabats are steeper than the isotherms. And so we've already seen isotherms. But what if this gas starts to condense and turn to a liquid? How could we draw that? And so let's say we shrink the volume, and we're on this isotherm, and at this point it starts to condense and become a liquid. What happens to the pressure when I keep condensing this substance? Now remember, this is an isotherm, okay? So this would be the pressure of the gas above the liquid at a given temperature. And that's what we mean by vapor pressure. So this right here would become a constant. And over here, sometime later, it would hit like the liquid phase volume, and then it would all be liquid. And so we'll draw this, but this isotherm would come up, it would reach a flat plateau, and that would be the vapor pressure for the liquid at that temperature. So this would be, at a given temperature, you're coming along, you're condensing, you're compressing, and at this point, you start to form a liquid. And so there's liquid drops, you keep compressing it, and all you're doing is pushing the gas into the liquid state. And at this point, it's 100% liquid, and if you keep pressing, then you're compressing the liquid. And so that's what you would see if you saw condensation on these plots. And for an ideal gas, you never get condensation. So this might be the plots, the blue curves are the isotherms for the ideal gas. We never see this flat business because we don't have any condensation in an ideal gas. So let's look at a real PV diagram, or one that's more close to experiment, the one on the right. So on the left, you have the ideal gas equation of state where you never see condensation, and on the right, you see condensation. In this blue region, you have condensation, where you have the liquid and the vapor equilibrium. And so that's what we call LVE, liquid vapor equilibrium, in that blue region. And so in this case, this is CO2. So we're coming along here at 20 degrees C at point A, and we're compressing it. We're still at 20 degrees C at point B. It's all gas. At point C, we start to form some liquid CO2. At point D, we have roughly equal number of moles in the liquid and the gas state. At point E, we have 100% mole of the moles are liquid. And then we're now compressing the liquid. And look at the slope. It's much steeper because liquids are not compressible. In fact, the slope of that is the isothermal compressibility of the liquid, that thermodynamic term that we talked about earlier. And so here at F, we're still just compressing the liquid. Eventually up here, we'll see a liquid-solid equilibrium, where we would have, I guess, LSE, liquid-solid equilibrium, where it would be converting from the liquid to the solid. It would be a volume change related to the two densities of those two things. And then it would have even a steeper climb once it's all solid, because we're now pressing on solid CO2. And so this is what a PV phase diagram looks like. It's got this region where you have these flat spots here. This is the vapor pressure of liquid CO2 at 20 degrees C. And that vapor pressure is 60 atmospheres. So someone multiply 14.7 times 60. Grab a calculator or use your phone. So 14.7 times 60.
Uh, 882.
Okay, so that's 882 psi. That'll just be something that you're maybe more familiar with. You air up your tires, and this is a pretty high pressure. Okay, my tires they take like 50 psi. It's a big truck. So, okay, so what is the vapor pressure at 0 degrees C? It's way down here, so it's like 35. So what's 35 times 14.7?
515.
515. So even at 0 C, liquid CO2 would have a vapor pressure of 515 psi. Okay, so yeah, it's kind of high. Above 31.04, you don't have any liquid CO2. So this is the critical temperature. This little star here is the critical point. You have a critical pressure and a critical volume. And notice above that, there's no blue region. And so at 40 degrees C, you just have this isotherm. It has kind of a wiggle there, but now you've gone from sort of the density of a vapor to the density of a liquid. But you don't ever see a meniscus. You never see it make two phases. It just gets more dense. And so we can zoom in on this, what I've drawn. So this is the CO2, same kind of diagram as we saw before. And you can see the ideal gas. So I've got a couple of temperatures on there that are the same. So 334 Kelvin for the CO2, that orange curve, and then the dashed curve is the ideal gas. So you can see as you get close to the condensation region, the ideal gas law is very wrong. Okay. So if you were to try to calculate your percent error, like right here, this would be the real pressure. This is the ideal gas pressure. So 140 versus like 85. So that's quite a bit of error. It's almost 2 times wrong. Okay, but out here, not so bad. So at large volumes, low pressures, high temperatures, the ideal gas law is not that bad. But when you get close to the condensation region, then it's going to be off. So what we have here now is we've got, so this is, This whole middle part of the course is about you being able to read phase diagrams, okay? And this is one of those things that I don't remember what it was like not to understand them. So that's a problem. I remember not understanding quantum. I remember not understanding some other things. So when I teach you those, I can see it from your perspective. I don't remember not understanding these. So it must be difficult for you to understand what I'm trying to tell you. And I find that because the test grades in this section are typically low. Okay, so I'm telling you, you got to figure out how to read these. All right, so I've never given that kind of warning before, so maybe this class will be different. All right, that's good. All right, now you know. So look at the axes first. We have pressure on the y-axis, volume on the x-axis. Okay, and in this case, we've just taken volume and divided by the number of moles to make it moles per liters per mole. Okay, so this is molar volume 0.6, so that's 60% of the volume 1 mole would take up. Okay, so you could convert that. If you had 1 mole, you could convert that to liters by multiplying by that 1 mole. So then over here on the right, we have large volume. We're compressing if we go left. So it's the same kind of PV plot we've been dealing with in the past, but we've got condensation going on. And so over here on the right, so these curves are isotherms. All of those are isotherms. Even the ones that go through the condensation region are isotherms. Make sense? Okay, that's good. Different temperature. Every curve is a different temperature. And this point here, look what this is labeled as. The volume of the gas phase at 258. So that's the temperature of this isotherm, 258. So that's the volume of gas I have in the container at 258. And if this is my volume, I'm all gas. Okay. What if I'm at this volume? I've got a mixture of some gas phase and some liquid phase. So this is the volume of the liquid at that temperature. And so what do we do right here when we have this container? This is a fulcrum. So let's talk about the lever rule. So let me switch this over. Here, we've got a 5. And so if we have the volume of the gas phase and the volume of the liquid phase, and we're on some isotherm, and we have a piston, okay, and we have our gas in there, and we're compressing it, and we're maintaining the temperature, and we get to here, that's the last point where we don't have any liquid in here. Okay, so let's go all the way over here to this one. So this is that point. Let's draw our same piston. Oh, sorry. So we've compressed it down and it's all liquid in there. Okay. What are we going to see in the middle? We've gotten condensation everywhere. Actually, I'm going to draw some at the bottom. So we got, as soon as we start to press beyond this point, we start to get condensation. We get little drops on the container walls, on the piston surface, and maybe even some has fallen to the bottom and made a meniscus. And so here, at this point, we've got about half the number of moles in the liquid state and half the number of moles in the gas state. If we keep compressing that piston, we just move over here. until we're all liquid. If we start pulling that piston back, then those liquid drops start evaporating. We get over here and it's all gas. So that's the vapor-liquid equilibrium. We can move back and forth with our piston, and we can go to all gas or we can go to all liquid. Okay. Let's say we're over here. Okay, let's draw this again. Let's say it's not in the middle. The middle's easy. If it's in the middle, you know it's 50-50, right? What if it's off to one side? Which side has more moles? Think of this as a seesaw. You ever remember, like as a kid, the seesaw? When I don't know, did y'all ever have seesaws?
Yeah.
You did? Okay, because I know they're taking all the good stuff away. They don't have carousels anymore. You know, the seesaws are dangerous. What do you know, whenever someone comes up and says, you want to, do the seesaw? We had one at the ballpark. What's the first question you ask them? Or like the ground rules? What do you say? Let's see if y'all use the same thing that I did.
How much do you weigh?
Well, that's maybe one thing, but you might just have to figure that out. It's one scoot a little closer up, so that you could still go. But the other was no offs.
Oh.
Right? So you're like, no offs? No offs. Okay. And it's kind of a promise. You're depending on them not to jump off. And you go, bam. Yeah. So no offs. So over here on this end, we've got the big guy. Okay, and on this end, we got the little stick man. Because look where the fulcrum is. Okay? And this means more moles, right? So if my volume is here, it's mostly liquid and a little bit gas. Okay? And so you can look, what would make that seesaw balance? I have to have a big mass on this end if the fulcrum's this far over. Okay. In fact, you could take this length here, length 1, and compare it to length 2, and number of moles in 1 and in 2. And L1 in 1 is equal to L2 in 2. So you could figure out, the ratio of moles using the ratio of the lengths. And that's called the lever rule. Okay. So this is one example in our phase diagrams where the lever rule applies. There's a bunch. Okay. And so, okay, so now that lever rule would apply in that vapor-liquid equilibrium region. So over here on the right, we have gas. So this is your interpretation of the, of the PV diagram. Far right, we're going to have gaseous state. All the way to the left, we have the liquid state. In the middle, we have the mixture. And then up above that critical point, we have the supercritical fluid region. So it's got to be a higher pressure than the critical pressure. It's got to be a smaller volume than the critical volume, and a higher temperature than the critical temperature. So what are the properties of a supercritical fluid? They have the density of a liquid, but they fill the container and flow like a gas. So you don't have to pour them. You could open a valve at the top and it would flow up and out like a gas does. But it has the density of a liquid. And there's no meniscus. Now this is really good because you could use it as a solvent, but it would fill the whole container. There's no meniscus. And so they use supercritical CO2 because it's cheap to do lots of things. Some big companies use it to dry clean clothes. It's like you put the clothes in a big stainless steel vessel, close the lid, turn the crank and tighten the clamps down, and then you fill it with 100 atmospheres of CO2 at enough, enough moles that it's, below the molar volume of 0.2 roughly. And then the grease is soluble in CO2, so the grease comes out of the clothes. Open a valve on the top, it takes all the grease over another container, pop a valve, and now the pressure is released, the CO2 flows over here, and the grease drops out of solution because it's not soluble in a gas, it's soluble in a liquid. So it's soluble in the CO2 solvent when it's a supercritical fluid, but the grease doesn't have a vapor pressure. It's not going to mix with gaseous CO2. So that's one way to use supercritical fluid. Supercritical CO2 is also useful for doing the same thing with caffeine and coffee beans. So that the caffeine is soluble in the supercritical CO2, but all of the water soluble stuff that we want to drink stays behind mostly. And so you can pull the caffeine out with supercritical CO2, put it to another container, pop the pressure, and then out comes the caffeine. It's been purified. Then you can sell that to Monster and all these other folks, Red Bull. So it's just a great solvent. It's inexpensive, and it's by nature recycled. You have this in a closed loop system of compressors. Yeah. So this is talking about the critical constants. Substance above those critical constants or below that in terms of volume is the supercritical region. Pretty useful. And once again too, it's the solubility in CO2 is a unique solvent, and so they even have chromatographic systems based upon supercritical CO2. So you can have supercritical high performance liquid chromatography. So you'll see that occasionally. So here are the critical constants for various gases or substances. So you see for water, we've got to go up above 218 atmospheres. That's a lot. Okay, 100 atmospheres would be 100 times 14.7, so it's at 1,400 psi, and this is 200 times that. So the volume, 55 mils per mole, so it have to be compressed into a space below, 55 mils if it was 1 mole of water at 218 psi and at a temperature of almost 650 degrees. So water's a long way from its supercritical region. But look at like hydrogen, 13 atmospheres, 65 mils, and 33 Kelvin. Or helium, 2 atmospheres and 5 Kelvin. So we're definitely, in the range of being close to the supercritical constants for helium. We just have to cram a lot of it into a small space and raise the pressure just a little bit, 2 atmospheres. Now, there's some other temperatures in this chart called the boil temperature. And so let's explore what that is. If you were to take this PV, so you have a container, so you've pretty much got a fixed volume, and you measure the pressure, and you have a number of moles in that container, and you have a temperature, and you take the pressure times the volume and divide by nRT, an ideal gas would give you 1, wouldn't it? Right? Because PV equals nRT. Makes sense, right? So this compression factor, Z, is 1 for an ideal gas. And so it's a great measure for non-ideality. So you take a gas, you stuff it in a container, you set the temperature, and then you measure the pressure. You say, okay, what is the pressure of this container? Is it lower than I expect, or is it higher than I expect? Right? So this thing could be less than 1 if it's lower than you expect, and greater than 1 if it's higher than you expect. If it is 1, you've got pretty good behavior. It's ideal gas-like behavior. And so you can look over here on the right. We can look at those pressures, and you can see that the compression factor at these different pressures is less than 1 in some regions and greater than 1 in others. You see hydrogen here is almost always greater than 1. But methane here, there's a region where the pressure is lower than you expect. That kind of means that methane, and here's ethylene, and here's ammonia, those are easier to compress than you would expect because of the attractions of the molecules. So they're hitting each other and kind of sticking to each other, so that means that they're hitting the walls with less pressure than an ideal gas. So these would be easier to compress, and this also tells us that hydrogen is like the worst to compress. There's not a lot of electrons to set up those instantaneous dipole moments, so hydrogen is really the least compressible gas. And so you can plot all of these different gases, their real behavior using this compression factor, and you can see their non-ideality. Now at the boil temperature, so that previous chart showed the boil temperature, at the boil temperature, you're at the right temperature where for at least a a fair range of pressures, the compression factor is 1. So if the gases have at lower temperature a lower compression factor than you expect, then you raise the temperature. You could go too far and they have a higher pressure than you expect. Then if you come back down, there's going to be a sweet spot, a temperature where they behave ideally for quite a while. And so you can compare different gases with their boil temperatures to kind of see how ideal they are. Now this is an interesting thing. If we think about gases and we just think of the terms of the attractions and repulsions, so we don't get mixed up in what kinds of attractions those are. We just say at some temperatures the gases are sticky, other temperatures they don't like each other, and so let's try to figure out if we can normalize these attractions. So we've measured the different gases and we measured their critical constants. What if we took the pressure that gas is at and divide it by its critical pressure, and the temperature divided by its critical temperature, and the volume divided by its critical volume? So we're sort of scaling everything by its critical constants. And so you have pressure over pressure, and so the units cancel out. You have temperature over temperature and the units cancel. And so this is a practice that's done in engineering a lot, and you might, if you're ever talking to engineers or at a presentation where an engineer's presenting their work, you might hear them say a very, very confusing phrase. They would say, this is plotted in unitless temperature or unitless pressure. And that's weird, isn't it? You're like, what's going on? Well, anytime you have something like unitless temperature, unitless pressure, you're just taking a scaling factor. You're taking a constant that's a property of that molecule and you're dividing by that property. So we're taking the temperature of the molecule and dividing by its critical temperature, and the units cancel, so that's unitless temperature. And this is the principle of corresponding states, that if we take these, we call them reduced variables or unitless variables, we take pressure over PC, volume over VC, and temperature over TC, then the gases behave similarly. So if we take that compression factor plot and we plot all the gases with their reduced variables and not their actual temperatures and pressures, then they fall on the same plot. And so this is absolutely amazing. So look at this plot on the left. That's the compression factor on the left and unitless pressure on the x-axis. And all of these gases, so this would be for the reduced temperature of 1. So that's at the critical temperature. And all of these squares, open squares, circles, and open circles fall on the same line, and that's nitrogen, methane, propane, and ethene, all behaving exactly the same. Isn't that cool? So that's why engineers love this, because if that's the property of gases, then I want to know how, let's see, hexane is going to behave. I just need to figure out hexane's reduced temperature, and I know what its pressure was going to be. So this is sort of an equation of state for all real gases, using their reduced variables. Now, one practical thing that we can do with this is to say, as in our automotive fuel exercise, at what temperature and pressure would hydrogen behave like hexane at 1 atmosphere and 298 Kelvin? So let's figure out what the reduced variables are for hexane at 1 atmosphere and 298. We divide by its critical pressure and critical temperature. So the reduced pressure and the reduced temperature is 0.03 and 0.58. And then now we take those same reduced variables and apply them to hydrogen. And then we put in the hydrogen's critical values, and then we solve for the actual. So hydrogen's actual pressure would have to be 0.4 atmospheres and 19 Kelvin. But if you were able to live in a world that was 0.4 atmospheres and 19 Kelvin, you could fill your tank with hydrogen, liquid hydrogen, just like hexane. Okay, so this is what we're saying. These reduced variables allow us to compare the behaviors of different substances. Now that's not realistic, but it's an example of how you would use these reduced variables. Okay, we've got about 6 minutes, so let's go over the exam.